Hello and welcome to DSAWeekly's Module 1's Medium Challenge Problem Tutorial. So today we have a good problem with us. It's called the Primality test. So what we need to do is we need to check if the given number n is prime or not. So many people, when they start doing competitive programming, this is one of the many questions that are given to the programmer to develop their skills in logical thinking. Alright, so it's pretty simple. We know what prime numbers are, and in our two base cases we can see the input is 5, so it's a prime number. We can just tell it by looking at it. It's something in our memory. Obviously a computer doesn't know about it, so we need to develop an algorithm. Similarly with 4, the output would be no, because 4 obviously is a composite number. Now the expected time complexity is O(n) by 2, or it could also be O(n), right? So since this is a medium problem, there's another way of doing this to reduce the complexity more till n by 2, but that would come in the hard part. So we'll just focus on if you can get it going from higher complexities to linear. Okay, let's begin. Alright, so one of the approaches we could take is what's called the naive approach, which is the easiest and the most the common strategy most of the programmers take. So it's very simple. Let's say I have a number n. In this case, let's call it 23 for example. Now there's a little algorithm, a mathematical definition in prime numbers that if we want to find out if a number is a prime number, what we look at is if that number modulo something, let's call it I for some time, if it becomes 0. If it is 0, what it means is that n is basically dividing the number I, right? Which means it's not a prime number, because a prime number is defined as it's not divisible by any number except 1 and itself, right? So what the naive approach would be, that we could just iterate starting from 2, because it's the first prime number, and go on till square root of n. Why square root of n? That's a good question, because look, if we have a number, we can write it as the product of its square roots, right? So let's say if I take 12. So yeah, coming back to the naive approach, what we can do is we can if we look at 12, right, so it has a lot of factors. You could go for 3 and 4, you could go for 2 and 6, right, and 1 and 12 and so on. Now what you can notice is that you cannot have two numbers, two factors which are greater than the square root of 12. What does that mean? So what's the square root of 12? It is around 3.4, around that number. So as you can see, no two numbers at the same time can be greater than 3.4. So if you see 3 and 4, 4 is bigger, it's bigger than 3.4, but 3 is less than 3.4. Not both of the numbers are mutually not bigger, they're smaller than the square root of 12. So what we do is in the naive approach, we iterate in a for loop and we go from 2 and all the way to square root of n. So simple for loop, I equals to I less than equal to root n and I plus plus, and what we check, very easy, we check if this condition, if n mod I equals 0. If this is the case, it means that n is not a prime number but a composite number, which means it is divisible by I, so it technically becomes composite. If we use this algorithm, we can actually see the complexity. It is of square root n. It's not linear, it's O square root of n. And what this means is it's more dangerous than On. We really don't want to go to O root n rather than On. So what could be the next approach? Yeah, so what should be our new approach? Well, we can use recursion, and by using recursion, we don't need to go over every number from 2 to root n. We just need to achieve a breakpoint when we need to return our values, and recursion is the best powerful tool you can use for that. So it's very easy. What we'll do is we'll write a function called check prime or something like that is prime. What we'll do is we'll declare what's called a static integer. What's a static integer? It means that let's say you give it the value of 2, right, and you're done with the recursion call, pura function ho gaya. You call the function again. What happens if it's not a static number? It stays 2, it initializes with 2. Let's say at the end of this function I increment the value of this static integer by 1, so 2 becomes 3. Then I exit the function, I call the function again. If it's not a static integer, it will go back from 3 to 2, but since this is a static integer, it stores that value 3, and in the next iteration at the end it becomes 4. Then we call it again, it becomes 4, and at the end becomes 5. That's what we want to do. So instead of using a for loop, what we are generally doing is calling recursion calls on a stack counter, and we'll just check the criteria if it actually is working. So let's go to our coding IDE and check out how it will be implemented. Alright, so we are on our coding IDE. What we want to do first, obviously, it's just use our bits std c++.h header file. It's a convention, so we have to use it. Now int main will only be used to call our function is prime check prime. So I'll just write cout is prime, right, and I'll give it 23, and I'll also call is prime and I'll give it the number 102, for example. Let's just do that, right. Now what we'll do is we'll write our function, and what we want to do is we either want we could use a boolean function. It just returns true if the number is prime, or returns false if it's not a prime, right. You could also use string, return a string, return is prime or not prime. We'll use bool in this case. So bool is prime, we'll take an integer n. Okay, now what we want to do, we'll declare our static variable, that is static int, and we declare it with basically, yeah, we declare it with starting from 2 because it's the first prime number. Now since this will be a recursion call, we need to handle base cases. What are base cases? So let's say if after multiple recursion calls a value goes to 1 or 0 or maybe less than 0, how do we handle that? So these are called base cases. So what we'll do is we'll write an if statement. We'll just check if the number is 0 or if the number is 1. If this is the case, we'll just return false, because in both of these cases there is no definition of prime number. 1 is a composite number and 0 is not even defined prime or composite, right. Now for our next turn, this will be checking if the number is prime or not. So what is the logic? After every recursion call, the value of I goes up, right, goes on to n, and we want to check if at a certain recursion call, if the value of n, our prime number, is equal to I. If that is the case, we'll return true, and the reason is that we have found that n is equal to I because it was never divided by I and it just equates to I, which means it has gone through all of the possible dividends, right, divisors. So n becomes I, which means it's a prime number. And for our last case, what we want to do is we want to check if n mod I equals 0. The classic example we saw in our naive approach, right. So what I want to do, I just want to return false. The reason, because I divides n in this case. It's pretty easy, right. So this was our last conditional, and what we want to do is after every recursion call we want to increment, before every recursion call we want to increment the value of I, so it goes till n, and in the end we just return is prime and with the number n. simple recursion call. So as you can visualize, let's say the number is 23, right? So it starts from I equals 2 and then it checks 3, 4, 5, 6, 7. Now what happens at 7? It's 23. Okay, it's 23. So it goes on till 23 and now n is equal to I. So it just returns true. It's a prime number. If we talk about 102, so in the first iteration what happens is it sees that okay, the number is divisible by 2. 102 mod 2 comes out to be 0, which means that 102 is divisible by 2. So it's not a prime number. Let's now just run our code and check if we are right. Okay, so it returns true and false. 1 and 0. 1 means true, 0 means false. So yeah, in our first case, the function returns 1, which means 23 is a prime number, and in our second one, it returns 0, which means it's a composite number. So this was the primality test. And if you talk about the complexity of this, it will be ON, which is linear. Why ON? Because as you can see, after every recursion calls, the worst case scenario would be our n being a prime and not being divided by I at any point in time. So I increments plus 1, plus 2, plus 3 and goes on till n. That's when our code checks if n equals I, then it returns true. So in the worst case scenario, our complexity becomes linear. So we just came from square root n to n, and that's a huge win for our code. This was the solution for the medium challenge problem. Like the video and subscribe to our channel. Thank you.